Okay, so thank you very much for joining us for this afternoon tutorial. It will be presented both by Professor Mohamed-Slim Alouini and also by Professor Salman Bashir. The title of this tutorial is New Trends in Free Space Optical Communications. I will briefly present the lecturers. Professor Mohamed-Slim Alouini was born in Tunis, Tunisia. He earned his PhD from the California Institute of Technology, Caltech, in 1998, before serving as a faculty member at the University of Minnesota and later at Texas A&M University in Qatar. In 2009, he became founding faculty member at King Abdullah University of Science and Technology, where he currently is the Al-Kawazimi Distinguished Professor of Electrical and Computer Engineering and the holder of the UNESCO Chair on Education to Connected and Unconnected. Dr. Alouini is a fellow of the IEEE and the Optica, and his research interests encompass a wide array of research topics in wireless and satellite communications. He's currently particularly focusing on addressing the technical challenges associated with information communication technologies in underserved regions, and is committed to bridging the digital divide by tackling issues related to uneven distribution, access to, and utilization of ICT in rural, low-income, disaster-prone, and hard-to-reach areas. Professor Salman Bashir is a senior member of the IEEE, and he is a lecturer in the School of Computing Engineering, University of Huddersfield, United Kingdom. From 19 to 23, he was a postdoc fellow in Communication Theory Lab at KAUST. From 2017 to 2018, he was assistant professor at the Electrical Engineering Department at the National University of Computer and Emerging Science in Lahore. He got his master's and PhD degrees in electrical and computer engineering from Purdue University, West Lafayette, Indiana, US, in 2014 and 2017, respectively, where he was a recipient of the State Department Fulbright Science and Technology Award. Dr. Salman's current research interests are the application of three space opticals non-terrestrial communication networks. He's currently serving as associate editor of IEEE Communication Letters. So, Professor Slim, Professor Bashar, you can assume the floor. Thank you.
Thank you, Luciano, for this very nice introduction. So we have some slides. I think Salman is going to upload the slides.
Right, yes.
And then I'll try to see if I can move them from my side. I guess no, I cannot move them.
Okay.
I guess only you can move them, Salman.
Okay, right, I'll do
That's
that.
fine.
Right.
We'll do that. So as Luciano mentioned, this tutorial is going to look at a technology that we cannot call new because it has been there for many decades. But I would say that, and I'll explain why, that there is a revived interest in this technology. And with that, ourselves, like Salman and myself, we have been collaborating over the last few years on this topic. And there is actually a good community of researchers who have been looking at new trends and new interesting problem for FSO. And that's why I really believe that there is a great potential for this technology in the coming few years. So let's go to the next slide, Salman, please. So this is the outline of the tutorial. So basically, we'll kind of motivate why free space optic communication is interesting, why it was always interesting, but maybe why actually also it didn't pick up for a long time, but why, meaning the challenge that it faced over the few past decades. And the advances in science, technologies, methodologies that are allowing FSO to kind of, let's say, meet or solve some of these challenges. And then also we'll talk about the new opportunities that are opening up with non-terrestrial network. We'll be focusing on this aspect that make FSO more attractive. And then we'll go together with Salman mainly going through different applications of these new scenarios where FSO is becoming trendy in the context, again, essentially of non-terrestrial networks. So we kind of go and examine every single scenario, really define the problem, motivate it, explain how the problem was solved, and kind of try to interpret results and explain a little bit the main lesson learned from every analysis. So you see here some kind of problem related to pointing acquisition, very critical in the context of FSO. I will explain that. Tracking also is very important. Optical, how to choose the optical, the optimal for detector size, and then eventually how we can apply FSO in the context of localization of UAVs, placement of UAVs that are acting as relay of optical wireless backhaul, and also this kind of optimization of the trajectory of UAV when you assume that they are laser powered. So maybe these are things that are not very well defined now, just like keywords and titles. But as we define every single problem, hopefully the problem will be hopefully will be clarified and explained in details. Yeah, let's go to the next slide. So again, FSO is being revived, and I will again explain that more later on because I want to start with terrestrial application. So when FSO started, so FSO, by the way, let's start from basics. We are talking about laser link transmission, not over fiber, but over free space. That's what free space optic is a directive collimated optical beam. There are multiple interesting wavelengths that where absorption from atmosphere is minimal. The two most popular one is around 850 nanometer and 1550 nanometers. But actually the 1550 is even, both of these, by the way, wavelengths are interesting because, first of all, you have minimal atmospheric attenuation around these two wavelengths, but also because they are actually matching very well with the wavelength or the window that we use for optical fibers, which means we can use essentially off-the-shelf photonic equipment to design our free space optic systems, given the popularity of fiber optic communication systems. Now, one aspect we have to take into account is that essentially beyond 1400 nanometer, above 1400 nanometers, you have less restriction from an AI safety perspective on laser beam transmission. Because when you are above 1450 nanometer, you are at a lower frequency, and basically you are allowed to transmit at higher power for lasers. And that makes the 1550 nanometer pretty much the most popular window of laser transmission for free space optical communication. So that's kind of a general kind of background on what is FSO and over which kind of wavelength we are operating. It can be used essentially for point-to-point because we are talking about narrow beams. This is not for access. It's more for point-to-point type of transmission. So backhauling, fronthauling. It can be for two terrestrial points, ground to air, air to space, space to space. All kind of point-to-point combination can be basically envisioned with a free space optical link. Next slide. Now, why there is interest in non-terrestrial network? I guess, or I hope at least, but like yesterday presentation kind of was good perspective on the importance of non-terrestrial network in today's world. If you want to cover wide areas, you want to gain altitude, you want to have basically base station attached to high platform station, as discussed yesterday, or satellites. And with that, we have seen this emergence of non-terrestrial network. And again, non-terrestrial network is different altitudes, HAPs, satellites. Of course, traditionally, or like the classical way, to connect these flying platforms is to use RF solutions, Ku band, Ka band, even Kv band. But of course, you need the higher, let's say, the bandwidth you need or the data rate you need, the more ground station would need. RF suffers from interference with terrestrial networks, limited spectrum. Secure communication may be a challenge because RF tends to be omnidirectional and can be eavesdropped, can be jammed. And that's essentially NTN if we limit NTN to the use only of RF spectrum. Next slide. So in this context, we can ask ourselves why FSO can be popular. First of all, from a very simple bandwidth availability, clearly FSO has pretty much unlimited bandwidth availability because you are tapping into the optical band, which is much bigger than the RF band. And it's unlicensed, so you don't need any approval. You can just use it, and basically it's not regulated, at least so far. So it is very interesting to rely on this band for non-terrestrial and even terrestrial application. So you are basically kind of using a fiber through the air, a type of technology with 10 terahertz bandwidth, essentially no spectrum limit and no spectrum regulation. Another very important aspect, and this is actually what made FSO very interesting in the NTN context. As soon as you start talking about non-terrestrial network, in particular flying platforms, drones, HAPs, satellite, the main constraint that aerospace engineers look at is a so-called SWaP constraint. SWaP stands for size and weight and power. How big is the payload, how heavy it is, and how much power it needs to execute its function, in this particular case, transmission and reception of information. And in this case, FSO is unbeatable. It is operating at much higher frequency, which means much lower wavelength than RF type of solution. So things are much more compact, much lighter, and much more energy efficient in the sense to get the same data rates. You can do it with lighter, smaller type of equipment. And that's what makes FSO very popular with the emergence of non-terrestrial networks. Just to make a long story short, to tell you this is not science fiction, Starlink, as we speak, is already using free space optic links to interconnect their constellation of satellites. So this is ongoing because that's the best way to kind of provide high-speed point-to-point connectivity, in particular in space where you don't have to deal with atmospheric turbulence, which we'll talk about them as we move forward. So again, with FSO, because of the huge available bandwidth, you don't need, at least as of now, develop very sophisticated signal processing approach to squeeze more data within the limited spectrum. This is what we do, as you know, in RF engineering and MIMO and all of these type of techniques in 4G, 5G, and also 6G. Because we are having limited spectrum, we need to try to kind of increase our spectral efficiency. With FSO, we have plenty of bandwidth, a very basic binary, basically IMDD, which is direct type of detection, non-coherent type of receiver, can be good enough to transmit at multiple gigabit per second. On the top of that, you can have a secrecy advantage in the sense we are dealing with a narrow beam. So basically, eavesdropping is much harder than with RF, where the beam is much larger and much wider. And again, because the narrow beam leads to more focus and a higher SNR of the receiver, so essentially you are more energy efficient. And one last aspect, and Salman will be talking about that towards the end of the tutorial. You probably heard, those of you very active, let's say in RF engineering, about the SWIFT concept. SWIFT stands for simultaneous, wireless, and information power transfer. Very nice concept, allowing to charge IoT device. But when you use it within an RF context, we are talking about tiny amount of powers. take the same concept and use, instead of RF, a laser, that's a different ball game. If you change swept by the so-called SLIPT, simultaneous light wave information and power transfer, you can transfer high amount of powers through a laser link. Good enough to basically sustain, for example, the proportion needed for a drone to fly. So this is a huge amount of power that can be transferred wirelessly, and that can be used for a variety of useful basically application, again in the context of non-terrestrial network. So all of this is making FSO more and more popular over the last years, again with the emergence of NTN and the need to rely on NTN to cover more of the uncovered areas. And that's why there is this revival interest in free space optics. Next slide. So this is an illustration courtesy of Mynaric. Mynaric is, for your information, a spin-off of DLR. So DLR is the German aerospace agency based in, at least they have few sites in Germany. One of the most famous one is in Munich, where they have very good free space optic technology for space. And at some point, some of the engineers dedicated the spin-off out of DLR called Mynaric, and they are now among the leaders worldwide on FSO for non-terrestrial and terrestrial networks. And this photo is coming from them, showing the difference between the size of a radio frequency beam and a laser beam. Clearly, there is, in terms of focus, a much big difference. In terms of, with that, you can translate that to energy efficiency in terms of amount of power you can transfer with the beam and data and so on. So that's kind of an illustration, a graphic illustration of some of the advantage of laser beam transmission. Okay, next slide. So bottom line, it's possible to think about feeder link of terabit per second, and especially if you are operating above the stratosphere. Remember, the stratosphere is at 20 kilometer altitude. Between 0 to 20 kilometer, you can encounter atmospheric turbulence, things that are not very friendly to free space optics. Above that, in space, when you have a HAPS talking to a satellite, a HAPS talking to another satellite, a satellite talking to another satellite, FSO is, as I mentioned in the context of Starlink, a perfect solution. The only issue you have to solve is the pointing, and we'll talk about that. And the more you enable inter-satellite links, inter-HAPS links, the less optical gateway station you will need on the ground. So that's always a trade-off that you have to deal with. If you are not allowing inter-satellite link or inter-HAPS link, basically aerial or airspace type of links, you would have at some point to kind of come back to the ground and go up because you cannot communicate inter-satellite or inter-HAPS. The more you allow this kind of integration or interconnectivity between aerial platform, the less you would rely on optical gateway station that maybe sometime you cannot put because you'll be flying over territory that are not under your, let's say, sovereignty, and it's not always easy to place these kind of optical gateway station or gateway station in general. So that's why having this inter-satellite, inter-HAPS connectivity is very helpful for many of these mega constellation in space. Thank you. For Salman, next slide. So again, FSO is a quite mature technology, especially for terrestrial application. We're not trying to hear some publicity, but these are the facts. Some of the popular, and we didn't put every single company here, but personally, I have in my lab some Tara equipment. So Tara is a spin-off of Google or Alphabet. They're based in the Bay Area. They have really a very good product, 20 gigabit per second, two-way communications up to 20 kilometer. It was used in Africa, in India. We used in Saudi Arabia to connect some islands that are 18, 19 kilometers away from the shore. Quite reliable. It's a technology that is mature. It has its issues like any FSO system. When there's fog and so on, it will fail. But there is the RF backup link that can help. You have also this TNO company. There is also another one we put here. I forgot the name. In Singapore, Mynaric has its own kind of terrestrial solution, Condor. So bottom line, and actually Condor is no, it's actually used also for aerial solutions and for space solutions. So these are all product that you can buy from the market and deploy, and they're not that expensive. Relatively, I mean, sorry, the terrestrial one are not that expensive. The aerial and space one are still quite expensive. Actually, the Mynaric type of device are still quite expensive, but the Tara, relatively speaking, in the order of the, like the $20,000, $30,000 for transceiver pair, whereas when you talk about the Mynaric type of product for aerial solution, they are still because not massively deployed in the hundreds of thousands of dollars. Thank you. Next slide, Salman. I mean, there are many papers that kind of demonstrate how fast you can transmit with FSO, and these are even some of them 10 years old paper, and there are probably even other records out there. But it's easy to reach few terabit per second using FSO over even long distance, like DLR were able in already 2016 transmit 1.72 over roughly 11 kilometers. And deep space, although we'll not talk much about it today, when you want to talk with the moon or with Mars, FSO being the most energy efficient technology is actually the way to go, and you can design systems that can communicate over millions of miles. So, as mentioned, FSO is really great in the context of non-terrestrial network, air, space, airspace, space, air. All of them are very good. It's already being, of course, used by NASA, DLR, ESA, the European Space Agency, the Japanese, SpaceX for their intersatellite links, OneWeb. Not now, my best knowledge, but in the future, so is the Lightspeed Canadian constellation. So this is kind of a technology that already for space is really part of the ecosystems. Now, the terrestrial FSO market is growing, but we have to be honest and say that it's still not massive comparative to, like, let's say 4G, 5G, and so on, because it's still a niche area, and RF is still very strong in the terrestrial network, and they don't have the same constraint from at least a swap perspective than in space or air. Okay. Now, what are the problems that FSO has to face? As I mentioned, it has to be line of sight. You cannot tolerate any blockage. So in terrestrial application, a building, a tree, a hill can be a problem. You need to have a line of sight. In the context of ground to air or ground to space, clouds, and the only way to solve this is using space diversity. So if you are having a ground to space or ground to air solution, if you are blocked from one particular location, you have to rely on a different location, few hundred kilometers away, to connect to the same kind of flying platform, let's say a satellite. Atmospheric turbulence is really also a problem in the lower part of the atmosphere for terrestrial application or for ground to air or ground to space. The few basically kilometer is the main challenge because it's basically when you go to these turbulences, what you see that the optical wave, as it goes, it goes going to bend over these different layers, and at the receiver end you have beam spreading and beam wandering. So beam spreading meaning by that the beam is not focused anymore, and the beam wandering, the beam is not completely centered, is going to move around like this. So you need to mitigate that. So you need to use adaptive optics, advanced pointing acquisition and tracking algorithms. Basically, this what make FSO a little bit challenging, atmospheric turbulence, and in a way relate to that pointing error and misalignments. Next slide. No, before. Yeah, one slide before, yes. So, I mean, how to mitigate these challenges? I mean, one of the very basic things you can do for every FSO system, you can attach to it the backup RF link, not maybe operating at the same data rate, but it will maintain at least the minimal connectivity. So I can give you an example, very simple one. Last year, we deployed this FSO link between kind of let's say a coastal area in Red Sea Global. That's kind of a big Saudi project, 4 hours drive from our university to an island that is about 19 kilometers from the shore. It's called Shubara Island. It's a very nice new development there. There is nice reef in the Red Sea, and the Shubara Island is a touristic island where they want to develop tourism around reef exploration and diving and scuba diving and so on. So this island, when it was in construction mode, they need to connect it. So we had to collaborate with Red Sea Global Project. We had to connect this island to the shore, 19-kilometer line of sight. FSO was the way to go if you want to give a 20 gigabit two-way communications. We took advantage of this opportunity to do a propagation campaign and assess the performance of this link. What we end up having is a 99.8% availability over 6 months of the FSO link. Quite good. But for MNO, that's usually not good enough. They really want to have the 99.9999. So we had to put an RF backup link, which basically over the 6 months we tested the system were achieved. So we had the 99.3 or 49s after the dot. Basically availability with this backup RF system. That's a paper that's going to be presented next week in Globcom. So if you attending Globcom next week in Cape Town, South Africa, you will see that this paper talking about the usefulness of backup RF link to make FSO link more reliable, or basically to make sure that the connectivity is not lost for the small fraction of time where FSO link is not available. As I mentioned, site diversity is the way to go for ground to air or ground to space. When you are blocked by cloud or by some kind of other effect in the space, you need just to from above change completely the location of your feeder links and or optical gateway to be able to connect to the ground from a completely different location with no blockage on the way. Acquisition tracking, this is something where a lot of work has been done. Salman has been quite active. We have done some of the joint work with some of our students here. So we'll talk about that as we progress, how acquisition, tracking, pointing, making sure that the two ends remain connected is an important aspect of the research of reliability of FSO system. Next slide. Now, another aspect that is often needed when you have obstructions, you may need to have relays in the way. Relay can be done using, for example, drones for aerial solutions to kind of also deal with bad weather effect at strong attenuations. So as you'll see in the paper presented later on by Salman, we will talk about how drones can be acted as relay in this context, and of course how to deal with pointing errors, and how actually also we can take advantage of this infrastructure of relayed FSO links that can be used not only for information transfer but also for power transfer. Next slide. So let me maybe now give at least the first. I would like to do the first part of this paper, and then I would like Salman to conclude that part, and then go through other example. This is one of the early paper we looked at in the context of signal acquisition in narrowband free space optical communications. So yes, next slide. So as you see here, okay, so that's a paper published a few years ago, 2020. So acquisition is yeah. Next slide, please. So basically, acquisition is the time needed to completely lock the transmitter and receiver. So you have two terminals, terminal A, terminal B, that are talk to each other with an FSO links, but at the beginning they're not aligned. At some point, we need to kind of align them, lock them, and we need to acquire the signal. That's kind of what we are talking about. Obviously, you want to do that in the shortest possible time. You don't want to keep doing that forever. I mean, that makes sense. You have basically a deadline. Within a deadline, you want to make sure that you lock on the signal and start transmitting and receiving information. Now, how do you do that particular type of acquisition? There are many experimental papers, including paper by Kahn in Stanford, looking at different ways to scan the space. So let's assume you have a ground station trying to lock to a drone that is kind of in the space. So what you can do, you can basically try to, with the laser here, try to scan by doing either a spiral scan or a raster scan or rectangular scan or even shotgun. So these are different approaches that you can use to eventually lock on the photodetector at the receiver end. So let's visualize that on the next slide. So this is the problem we have in place. So basically, what you see here in red is the receiver telescope, the footprint, let's say, of the beam. And you have the kind of big inserted region over which we are trying to find where is the detector. And assuming a spiral scanning path, which actually is the best path based on our study, you will go through, you start from here, from the center. That was kind of your best guess where the photodetector is, but actually you keep going around up to a certain point until you think you are beyond the cover, like the inserted regions. You give up and you try again, because actually you may have found the detector, but you probably have misdetected it. Maybe the noise is too high and you cannot lock on the you have basically a misdetection, and you kind of don't lock into and don't kind of stop your acquisition time. So you want to minimize acquisition time, as I told you. So next slide. So the way you proceed. So you start with this kind of inserted region based on the roughly GPS or radar signal localization. Typically, it's like 3 times kind of sigma naught, the position assumed to be really distributed. And then next slide. So, of course, the beam footprint is another important parameter, depends on this angle. There is an optimal footprint. I mean, if you make it too big, of course, you lose in, let's say, sensitivity. If you make it too small, then you kind of takes too much to go through all the whole kind of inserted region. So there is an optimal, let's say, size of this footprint that will minimize acquisition time, and that was one of the main objectives of this study. So the way it goes, let's go to the next slide, is essentially you go through different scans. So you start from the center, you go around, and then if you fail to lock, you restart from the center. Every time you do a full trial, that's an attempt. The number of attempts is denoted by X, okay? So X is the number of trial until essentially the last trial, which is going to be successful, because at some point you will lock into your signal. So X is a geometric random variable, is the number of basically unsuccessful full scans, okay? I mean, actually, Y is the time spent in unsuccessful full scan, which is X multiplied by the time needed for full scan, TS. So TS times X is Y. X is a very simply geometric random variable. And then V is kind of basically the fraction of time you spend in the last successful scan to locate the receiver. So it's like over a fraction of the whole search. Now, you can easily show that V actually is exponential random variable. So what you end up solving to get the total acquisition time is this very basic probability problem where you have basically Y, which is a discrete geometric random variable, added to a continuous exponential random variable. So basically distribution of Y is geometric, given by here. Next slide. Distribution of V is exponential random variable, given that the position is following a Rayleigh distribution. So basically, you have the sum of two and dependent random variable, one discrete, one continuous. The sum of this distribution is going to follow convolution, as you know. You convolve a geometric random variable by an exponential random variable, you end up with the CDF that Salman derived, given in equation 2, that is function in particular of the dwell time, and as well as the important other parameters, the beam footprint. So if you plot this acquisition time, so this is just mathematically speaking, what this is the probability that the acquisition time exceeds the threshold, which means that violates deadline. Let's assume put yourself a deadline. If you exceed gamma times, nanoseconds or milliseconds, to acquire the signal, you are in violation. Basically, you have to drop some packets. This is a closed form expression for this violation time as function of system parameters such as the time needed for scanning, the probability of detection, the dwell time, as well as a beam footprint. Next slide. So I think I'll let you continue here, because that's part of the. I want to, Salman, you have been more involved in this analysis to talk about the probability of misdetection, which is a big important parameter, and how based on that and the beam footprint, you can find the optimal value of the beam footprint to minimize acquisition time. Go ahead, Salman, please.
Thank you, Professor Slim. Right. So in this case, we're looking at the photon counting receiver, because we are trying to acquire the terminal, and so we're looking at these very sensitive receivers, or detectors that can basically work with even single photons, right? So in this case, if let's say you have an array of detectors that's used to sense the signal from the ground station, right? So in that case, this signal will generate some photons in the detector array, right? So in this case, this random variable ZM is the number of photons in a certain detector in the array, and alpha m is the weighting factor, right? So multiply this and compare that with a certain threshold to compute if we have a signal detection or not, right? So in case we have a missed detection, or if this signal stays below a certain threshold, we can compute its probability. So ZM is here. All these photon counts are modeled by a Poisson distribution. So this is a Poisson distribution with a certain rate. So this contains both the signal photons as well as the noise photons, right? So again, for maximum likelihood detection rule, we have optimal weights that we can take and multiply with each of the detector's photon counts, right? That will maximize this detection probability. Or in this case, this is the misdetection probability, right? So, or the probability that you do not detect a signal link. So this is the optimal weight, right, for each for multiplication with each photon count in a single detector, right? And so this is a function of the SNR in each detector, right? And so again, we have a number of constants that we can describe here, which is ks and this variable c naught, right? And the function qxy is the regularized gamma function, which is given by this expression, which is a ratio of the upper incomplete gamma function and the other gamma function, the regular gamma function, right? So in this case, the idea is that we compute the misdetection probability based on the maximum likelihood rule, right? So sorry, in the next slide. So we can compute, so we can plug in. So the idea is that p here, the small p, is the misdetection probability, or the probability that you'll fail detecting the receiver, even if you shine the light on that particular receiver, right? And so this of course we know from the previous slides that this complementary CDF, this the probability that the acquisition time will exceed a certain threshold, right, is based on this misdetection probability, which is p here. So we can see that when p is very small, right, so it's a good scenario, because your detection probability is of course 1 in this case. So we have to so for when p is approaching 0, then we have a very good system, right? So in this case, of course, the probability in this case, the probability that the acquisition time is greater than the threshold is approximately equal to this number, which is this exponential distribution, right? And so this checks out. So if you plug in P0 here, right, you're left with just this expression, right? And so this checks out with the fact that, when P0, when we have a very good scenario, then, the number of unsuccessful attempts is 0 with probability 1, right? And then the only acquisition time that you have is the time based on the time you spend in the final scan, right? Which is, so in this case, the total acquisition time will become equal to V, which is the time you spend in the successful attempt, right? And on the other hand, if you have a very poor scenario where your SNR is poor and your probability of misdetection goes to 1, right? Then effectively, if you look at these terms, right? So this will, of course, multiply with this term. So this will be 0, but then this term cancels with this term, right? So you're left with just P here, so which is almost equal to 1, right? So when P goes to 1, then the probability that you're above any threshold is 1, right? So this threshold can be any huge number, right? And still the probability is 1. So this is telling us that when P goes to 1, right, then you always are looking for the terminal, right? So, and you never complete acquisition successfully. So these are some, asymptotic scenarios that we looked at. And so the next, Presley, do you want to continue this or should I finish this?
Go ahead. No, go ahead. Yeah, it's okay.
Right. So we, like Presley said, in the previous set of slides, that the beam footprint, which is the radius of the beam that we have, right, plays an important role, right? So if the beam footprint is too small, of course, that's that's good for SNR. So you have high SNR, so your probability of detection becomes large, right? Or your P becomes your probability of misdetection becomes smaller, right? So that is good for detecting the terminal. But on the other hand, the problem is that if the beam footprint is too small, then you will end up spending more time while you're scanning, right? So the beam footprint depends. So this rho Z, this beam radius depends on the beam footprint, of course. So this determines the size of the beam, right? So if this is going to 0, then of course your number of unsuccessful attempts will minimize because your probability of detection has become very good, right? So you don't have any unsuccessful attempts. But on the other hand, you'll end up spending too much time during the final successful scan, right? Because your footprint is very small and you take a lot of time while you travel on the spiral itself. On the other hand, if the beam footprint is large, then of course your probability of misdetection will become large, right? Because your SNR is small. So in that scenario, your V will become small, of course, because you're covering because your beam footprint is large, so you spend less time on the spiral while you're traveling on it or while you're scanning it. But because you have now low SNR, the number of unsuccessful attempts will increase, right? So there's a trade-off here where you can find the best beam footprint that will minimize the overall acquisition time. All right, so if we plot this, if we go to the next slide. Right, so once, this probability, this complementary CDF, this is something we want to minimize because this is telling us that, this is the probability that you'll exceed this certain metric, this certain, time that's your deadline, right? So you want to minimize this. You want to make sure that your acquisition time is always less than this particular deadline, which is gamma, which is the threshold, right? So the end goal is to minimize this complementary CDF or this probability that the acquisition time is greater than this threshold. So if we look at this and so in this plot, we look at, different, complementary CDF values for different types of arrays, right? So in this case, we're looking at the fact that we have one array which is composed of only one detector, and then we have other arrays which are made up of more detectors, right? So given that you actually fix the area of the array, and if you increase the number of detectors in that array, right, so that's more helpful because if you increase the number of detectors, you end up with a more efficient sufficient statistic for detecting the signal, right? So we see that as you increase the number of detectors in the array, your complementary CDF performance improves, right? So for this is for m equals 4, and this is for m equals 16, right? So m being the number of detectors in the array, and so you get the best performance as some as you increase the number of detectors or elements in the array, right? And so this is the comparison of the complementary CDF as a function of noise power. And so in this figure we see that the complementary CDF of the acquisition time as a function of the beam radius, right? So here we see that there's an optimal beam radius at which your the complementary CDF is minimized, right? So for acquisition, we should choose the beam footprint more carefully, because there's always an optimal footprint at which you maximize the system performance in terms of acquisition. So now we go to the next slide, right? So in this case, so this is the paper we published right after the paper we discussed previously. So here the idea is that we can improve the performance of our acquisition system that we proposed in the previous paper, right? So the idea is that especially for these deep space type channels, that are very lengthy or very long in terms of their link distance. There, these link distances can be hundreds of thousands of kilometers, right? And so in deep space, typical optical systems, operate on photon counting receivers, or these single photon avalanche detectors, right? So these detectors are highly sensitive, and they can detect very extremely low levels of signal power, right? So these detectors, or these avalanche detectors, or these photon counting detectors, are very useful for long link distances in deep space, right? So in deep space, a problem, it's common to see the probability of detection being very small, right? So that number one, of course, these link distances are very small. So these link distances are very large, right? So they lead to very small signal power at the receiver, right? So at the receiver end, you only see a few photons during the observation interval, right? So, and of course, the second reason is that if you want to minimize the probability of false alarm, you have to raise the threshold of your detection, the detection rule, right? So false alarm means that you don't see the terminal, but the system tells you that there is actually a terminal present, right? Because the noise has exceeded the threshold, right? And so this is something we want to avoid, because we don't want to assume that the terminal is present and we start transmitting the signal in the direction of the terminal, right? Because otherwise we'll end up transmitting data to nowhere, right? So, and then of course we realize later on that, oh, there is no terminal present, and then we'll start the communication link again. So in this case, the idea is that because of the long link distances, which lead to low or poor energy, as well as the probability of false alarm being being set to low enough, right? The probability of detection suffers, right? So it can be quite low. So in this case, there's a chance that even if the terminal is present within the uncertainty sphere, right, you may miss it because you missed it because the probability of detection is quite low, and for your receiver, right? So in this scenario, what we proposed was that instead of going through the entire sphere, starting from the center and scanning every region of the sphere, we should focus more on the regions that have higher probability, right? So if you look at this this figure, so if I go back, so this is the uncertainty sphere in this case, right? And so the terminal is assumed to the presence of the terminal, or the location of the terminal inside the sphere is distributed as a Rayleigh random variable, right? So the probability that this receiver is present is closer to the center of the sphere is quite large compared to the scenario when the receiver is far away from the center, right? So near the center of the sphere, the probability that we'll locate or find the receiver is large compared to the probability that we find the receiver at the very end of this sphere, right? So we are counting on this situation, right? And then based on this, we will in this algorithm, right? So in this algorithm, so the idea is that you want to exploit this this prior information that the regions close to the center of the sphere are higher in probability, and the regions at the far away are lower in probability, right? So and the spiral, a regular spiral scan or an ordinary spiral scan is inefficient because it searches the entire sphere. It starts from the center and it keeps on looking for the receiver, right? And it continues until it reaches the end of the uncertainty sphere, right? So we wanted to propose an improvement on this, this regular spiral scan by coming up with this adaptive spiral search algorithm, right? So in this case, what we do is we divide the total uncertainty sphere, right, which is the big sphere outside, into a number of smaller error spheres or smaller uncertainty spheres, right? So the idea is that you divide the entire sphere, the big sphere, into a number of smaller spheres with these radii R1, which is smaller than R2, and so on and so forth. And this Rn is the radius of the full sphere, the uncertainty sphere. And so we have these regions, right? The region corresponding to the sphere 1, and then the region corresponding to sphere 2. So they are all subsets of each other. So SR1 is the subset of SR2 in this case. So this region will be SR1, and this whole region, it corresponds to SR2, right? And so on and so forth. So what we do is, in this algorithm, we start from the center of the first sphere, right? And then we'll do a spiral, right? And then once we reach the end of this sphere, right, we will not continue to the next sphere, but rather we'll come back to the center again. And then we'll start scanning SR2 in this case, right? So we'll scan again SR1, right? And then we'll enter SR2, which is the the region corresponding to the next sphere. And then we'll end at the very end of SR2 in this case, right? And if we don't locate the terminal, we'll come back to the center again. So again, we will not keep on traveling to the end of the sphere like we do for the regular, the regular spiral scan technique, right? So every time we end a certain sphere, we'll always go back to the center and restart the whole process, right? So, and of course, once we repeat the whole thing and reach the final sphere, which is the the ultimate uncertainty sphere, and we cannot locate the receiver still, we'll restart the entire process, right? So in this case, what we're doing is that we scan the center region, the region corresponding to the first sphere n times, right? Let's say we have n number of, we divide the total uncertainty sphere into capital N spheres, right? So in this case, the first sphere, the smallest one, gets scanned by n times. Then the next annular ring. So this is a ring now, right? This is a region SR2 minus SR1 is this region, right? So this gets scanned n minus 1 times. Sorry, this gets scanned n minus 1 times, and this gets scanned n minus 2 times, and so on and so forth, right? So the idea is that here in this algorithm, what we're doing is that we are scanning regions of higher probability more often than the regions of lower probability, right? Counting on the fact that the receiver is more likely to be present closer to the center of the sphere than the probability that is far away from the center of the sphere, because of this this Rayleigh distribution argument, right? So what we had this optimization problem that we needed to solve. So the idea was that you want to minimize this function, which is either the the expected value of the acquisition time or the complementary CDF of the acquisition time, right? So again, we had the constraint that all these of course radii, they form an increasing sequence, right? And the beam footprint is fixed at a certain value, and the received power is also fixed at a certain value, right? So these were the constraints. And And then so we looked at some. So these are some of the parameters that we use. The beam width, which is very small, 10 microradians, and the region of the sphere, it's about 2,500 meters in distance, right? And the transmit power was 2 watts, right? So again, for all these parameters, we got some results, right, based on the optimization problem that we solved. So this is the acquisition time, which is plotted with respect to the number of spheres that we divide our total uncertainty to the total sphere into, right? So let's say you divide the total sphere or the big uncertainty sphere into, you can divide that into 1, 2 small spheres, or 3 or 4 or 5 or 6 or 7, right? So in this case, we found out that the more the number of spheres you have, the better off you are in terms of minimizing the acquisition time, right? So this was one result that we got. And so again, this is the next figure, right? So in this case, again, we're trying to compute the complementary CDF. So again, the goal is to minimize this probability that you'll exceed the deadline, right, or this threshold. So this is again, the complementary CDF also follows a similar behavior that as you increase the number of subregions or the smaller spheres inside your bigger sphere, you will end up maximizing the system performance, or you end up minimizing this complementary CDF, or this probability that you'll exceed the deadline, right? And then so again, this is one scenario where this is these two plots. So the ones in the solid line, they are based on a uniform sphere system, right? Like this, right? So in this case, you're not optimizing these spheres, they're radii, right? So they are placed or they're formed uniformly within the entire uncertainty sphere, right? So this is the solid lines represent a uniform distribution, like all the annular rings, right? They have the same separation, right? So this is the uniform way of describing the uncertainty sphere, right? Dividing the uncertainty sphere into a number of spheres. So this is a uniform division, right? But of course, if you optimize these radii, right, then you'll end up improving the system performance, right? So in this case, if you look at this, so this is one scenario, right? One, result of the optimization that we did, right? So in this case, this corresponds to the fact that when the probability of detection is 0.08, so this is quite small, right? And so this is what the optimal spheres look like for this probability of detection, right? And if your PD is quite large, the probability of detection is quite large, then all your spheres lie at the end of the big uncertainty sphere, right? So in this case, this is telling us that the system has collapsed to, or the optimal system is the same as the regular spiral scan that we discussed previously, right? So when the probability of detection is quite large, when the system is doing very well, then the regular spiral scan will be the optimal thing that you want to use to acquire the terminal. However, if the probability of detection is low, then of course you will need to optimize your your search algorithm, the spiral search algorithm, and so you'll get a different scenario here, right? So in this case, we can see that this is this is not uniformly distributed, and you have to follow this scheme in order to maximize the system performance or minimize the acquisition time, right? So this was one result that we got. So another technique. So previously we looked at the idea that we have these spheres and we move along a spiral inside these subregions, right? So again, we're using a spiral technique to scan each of these smaller spheres inside the main sphere, right? But there's another simpler rule. I mean, there's another simple technology. You don't need to divide your uncertainty sphere into a number of smaller spheres, and you don't need to do a spiral scan. So all you need to do is you just shoot pulses randomly within the big uncertainty sphere, right? And then you hope that you locate the terminal. So this is going to be more simpler, more computationally simple because you're not pointing the beam in a very specified narrow direction or in a very precise location, right? So you're just shooting the pulses randomly within the uncertainty sphere, and you're hoping that the receiver will be shined by one of these pulses, right? So in this case, we compute the detection probability, the acquisition time, the mean acquisition time as a function of the detection probability, right? And we look at the fact that as you, of course, as you increase the probability of detection, the mean acquisition time and the complementary CDF will decrease, right? However, so this dashed line is based on the shotgun technique, right? So this is roughly in the it's doing quite well, but not as good as the spiral technique. I mean the spiral technique that we use for the the adaptive acquisition scheme, right? So in this case, we note that some of the conclusions were that the adaptive spiral technique performs better than the shotgun approach, especially when you divide the sphere into a large number of smaller spheres, right? However, of course, with spiral technique, you have to be very precise with pointing, right? So your pointing complexity, your hardware complexity will increase significantly if you are sticking to the spiral scan approach. So the shotgun approach is more simple to execute. Right. So now in the next set of slides, we'll look at, so we covered two aspects on acquisition in the previous set of slides. Now we'll jump into the beam tracking problem, right? Especially in the context of photon counting arrays. Again, these principles are universal in the sense that you can apply these to systems that do not use photon counting arrays. They are based on simple Gaussian systems, right, or Gaussian noise, where you have large signal and noise power, so you can approximate the photon counting process with currents, right? So in this case, but in deep space, of course, we have these photon counting systems. So we based our results on these, and so this was published in 2021. And so the idea was, so in any optical receiver, right? In most optical receivers that we look at, there is a tracking channel which is based on an array of detectors and a detection channel, right? So the detection channel is used for the detection of symbols that you transmit from the transmit side, and the array is used, or the tracking channel is used for tracking the beam, right? So the idea is that you have incoming light beam, right, which enters the telescope, and then it gets diverted by some mirror assembly, right? So we have these fast steering mirrors that can that can reflect the beam and send it in a different direction, right? So in this case, so once the beam enters the system, it can be split by a beam splitter, right? This is a more of a prism device. It can transmit, it can divide the energy and transmit those into different channels, right? So in this case, a beam splitter can be tuned to deflect alpha fraction of energy into the detection channel, and 1 minus alpha remaining portion of the received energy into the tracking channel, right? So this fraction of the total energy, which is 1 minus alpha times the total energy, right, goes into the array of this detector array that's used for tracking, right? And the alpha portion goes into a single detector in this case, right? I mean, you can replace this with an array of detectors if you want, but typically, in many systems, people use just a single detector, right? And so based on the output of this detector, you can detect what symbol was transmitted from the transmit side. Here in this case, so once you for tracking, you can with an array of detectors, you have access to the output of each of the elements of this array, right? And so you can take this output, and then after some processing, you can use some algorithm which is based on either centroid, maximum likelihood detector, right, to compute the location of the spot on this array, right? So again, so these algorithms will determine where the beam is on this array. So again, you have this incoming beam, right, which produces a spot on this array, right? So the spot location depends on the angle of arrival of the beam, right? So if the angle changes, the spot will move on this array, and you can sense the location of the spot based on the outputs of these detectors, right? So the detectors that have the beam or the spot on them will have a higher number of photons or higher current, right? And the spot and the detectors that don't, they are not under the beam footprint, they'll have only noise, so their current levels will be low, right? So based on this, you can determine where the spot is, and if you know the spot location, you can infer the angle of the beam, right? And so, or the direction of the incoming beam. So we can use different algorithms to compute the location of the spot on the array, and then we can feed that back into a controller unit that will drive this mirror assembly to reorient or readjust the position of these mirrors so that the beam can be aligned to the center of the array, and the beam can be aligned to the center of this detector, right? So if the beam begins to move away from the detector or the then this system will detect this beam deviation, right, and realign the beam to the center of the array as well as this detector, right, so that we can continue to get the signal, right? So here, so in the tracking channel, right, so again, this is the lens, right? So this is the telescope lens. And so what this lens does is, it takes the incoming beam, a portion of it, right, and it focuses that on the array, right? So again, this angle of arrival phi has a one-to-one correspondence with these parameters x0 and y0. So x0, y0 is the center of the beam, or the center of the spot on the focal plane, right? And so if you know x0, y0, then you can infer what the incoming angle of arrival is, right? So there's a one-to-one correspondence between the incoming angle of arrival and the location of the spot on the array. So, and of course, this angle is, a solid angle is, the sum of both the azimuth angle as well as the elevation angle, right? So in this case, you can determine, if you know what x0, y0 is, right, you can determine the angle of arrival. That's the main idea. And of course, this angle or the spot location, parameters x0, y0, they are time varying because they depend on the angle of arrival. And the angle of arrival, of course, it depends on the, different channel conditions. So it's always time varying in that sense. So this is what the spot or the profile of the spot looks like. So we typically model this with a Gaussian distribution, right? So typically the spot energy is pretty high, it's maximum at the center of the spot. And of course, it, decays or, becomes smaller as you move away from the center of the spot. And so in many cases, this is well approximated by a Gaussian function, which is given by this expression. Rho is the beam spread factor, or you can call this the beam. Some literature calls it the beam width as well, or the spot width or the spot size. So rho has many names. Again, this is a measure or a number that measures the spot size, right? And of course, x0, y0 is the center of this spot, which can deviate on this array. And lambda p over rho square is the peak value of the this laser spot or beam spot on the focal plane. And lambda n is the noise, a part of this this intensity, right, which is modeled as uniformly distributed. And this depends on the dark current as well as the background radiation. So in case you have high background radiation, right, so then your lambda n will shoot up, it will go up, right? So again, this is typically modeled as a uniform factor. This does not depend on the region of the array. So here we looked at some performance metrics, right? So again, if you can measure or you can estimate the location of the spot, like I said, in my previous slide, you can infer the angle of arrival, and then you can readjust or realign the beam, to the center of the detector, right? And so in this case, we can measure this spot position, right? Or in other words, we can infer the angle of arrival of the beam, right? And then so we want to make sure that we can measure this quantity as accurately as possible, right? So again, if the actual quantity is x0, y0, which is the center of the beam or the center of the spot, right? Then you want to make sure that the values that you estimate for your x0, y0 are quite accurate, right? So one measure is the Kramer-Rao bound, right? So here we see that we're trying to measure or estimate x0, y0 with this estimator, right? And so of course we have this is the deviation or the error, and the Kramer-Rao bound is here it's plotted as a function of noise power, right, for different types of arrays, right? So again, here we see that if we fix the area of the array and change the number of elements in the array, right? So let's say you have an array of fixed area, but if you increase the number of detectors, then of course the number of the area per detector will become small, right? So you can come up with different arrangements, keeping the area of the array fixed, right? So here we are plotting the Kramer-Rao bound as a function of noise power for different types of arrays. So the first array has 4 elements or 4 detectors in it, and then you can have 16 elements. So this will be more like a 4x4 arrangement, which is shown here, right? So this is an array of 16 elements or 16 detectors, right? And then of course you can you can have arrays of size 6x6 or 8x8, right, or even 16x16 in this case, right? So what we see here is that the CRLB or the Kramer-Rao lower bound performance improves monotonically as you increase the number of detectors in the array, right? So the lesson learned is that the number of elements you have in your array, the better off you are in terms of minimizing the CRLB. So CRLB or the Kramer-Rao lower bound is something you want to minimize. It's something you want to make as small as possible, because this is the mean square error of the lower bound on the mean square error of any unbiased estimator, right? So if you minimize the CRLB, you also end up maximizing the system performance, right? So in this case, we see that of course the CRLB is decreasing with the number of detectors in the array, but of course we also note that that there's a law of diminishing returns, right? So of course as you go from, let's say, 4 to 16, you see a big jump in the CRLB or a big reduction in CRLB. But of course, as you go above, the advantage or the benefits begin to reduce, right? So beyond a certain large number, it's not advisable to keep on adding more detectors, because when you have more detectors, you also have more complexity in your system, right? So more detectors mean more computational complexity, but that's not buying you enough performance in terms of CRLB. So there's a law of diminishing returns that's setting in, as indicated by this figure, and you do not want to use too many detectors in your array, right? So here, so this is another result that we found out. Again, this is very intuitive. So in this case, we are measuring the CRLB or plotting the CRLB as a function of the spot radius, right, or the beam radius. So here we have the CRLB as a function of the beam center on the array, right? So in this case, as you go from 0 to 0.8, you're moving your beam on the array, right? So assuming that the array is, extends from -1 to 1 millimeter, right? You can move your spot anywhere on the array and see what the CRLB looks like, right? So in this case, we see that the CRLB. So again, here we're comparing two types of arrays, right? One is composed of 16 elements. The other one is composed of 64 elements. And the area of these arrays is the same, right? So one has more detectors, the other one has a smaller number of detectors, right? 16 versus 64. So here we see that, if for a small beam radius, of course, for the large beam radius or the large spot size, there's no fluctuation in the CRLB. But for a small spot radius, we see that, there's fluctuation, there's peaks and troughs, right? And so these peaks and troughs are more prominent when the number of detectors is small, right? So what's happening here is, the following. So we have a trough here, or the valley, every time we cross the edge of any detector, right? So these troughs represent the edges of detectors, right? So, or the boundaries of these detectors, right? So let's say, when the spot is at the boundary, then it's easy to track the spot, right? Because the spot is now straddling more than one detector. And if it moves around the boundary, we can sense the spot more accurately, because any movement around the boundary will change the levels of currents in any two adjacent detectors, right? So we can sense the spot position more accurately when you are at the center of when you are at the boundary of boundary of any two detectors. However, if you're at the center, so all of these peaks, they correspond to the centers of the detectors, right? So in this case, for a 4 by 4 array, if and for this particular radius, the spot size, right? If you're at the center of the detector, right, then you're sort of localized within that detector, right? And so any movement within the center of the detector will not be registered by the system, right? So that's why the CRLB sort of shoots up when you're at the center of any detector or any given detector, right? So of course, when you have more detectors, then you're always the beam spot is always straddling a few small detectors. So any motion will be registered by the system, right? So in this case, so the idea is that, of course, we want to choose the spot size carefully. Otherwise, we'll see this fluctuation in the CRLB as the beam moves on the array, right? So the overall the takeaway messages, or the take home message is that, of course, for a fixed energy, you will end up minimizing the CRLB overall in an overall fashion, right? But you'll have more fluctuation if the spot size is too small. So you have to sort of match the spot size with the array of detectors that you have, right? So if you choose an array with a large number of detectors, you will also want to choose a smaller detectors, smaller spot size, for your array. And if the number of detectors is large, then you want to spread out the beam slightly so that you avoid these fluctuations. So, and of course, on the edges, the CRLB goes up. So these when you're closer to the edge of the array, the CRLB goes up because some of the energy is falling off the array. So your spot is very close to the edge, and not all the signal energy is captured by the array, right? So that's why your CRLB begins to shoot up near the edges of the array. So in the next set of slides, so this is again a paper we presented. We've got published in this
Salman,
journal. Yes.
Salman, I
Yes.
suggest because it's often hard for people to absorb all this material in one shot.
Right.
To take a small break now and maybe open the floor for questions, and
Okay.
then we take a small break, and then we continue the second half, which will include these kind of follow-up studies. But let's
Right.
maybe ask Luciano if there are some questions from the audience about what we just presented, and then take a few minutes break. That's my suggestion, at least. Luciano?
Yes, that's a good suggestion, Professor Slim. Are there any questions from the audience so far? We are checking also online, so just 1 second. So we don't have any questions so far, so I guess we can have like a 10 minutes break, perhaps.
Sure, sure.
Then
Yeah, like at the half of the hour, right? Like I think now maybe it's 4:30 or 3:30 in Brazil now.
it is 4:20 in Brazil now. We can come back like
Yeah, 4:30. Yeah.
4:30.
So we can meet 4:30.
Okay,
Okay.
perfect.
Okay.
Okay,
All
so a
right.
small break. Okay, thank you.
Thank
Thank
you.
you. Thank you. Bye bye.
Hi, professors.
Yes, hi.
Let's get back. Professors, feel free to continue. Take your time.
Okay, yes, Professor Salman, he will take it where we stopped. Go ahead, Salman.
Yes, Bruce. So in this, so welcome back from the break. So we are going to cover, slightly new topic here. So this is again related to, beam tracking. So the problem here, so this was published in Transactional Communications in 2021. And so here, so the idea was that, okay, in typical FSO receivers, of course, we know that, some energy will be deviated for beam tracking, right? And the rest will be reserved for symbol detection, right? So if we look at this figure, which is on the next page, again, I'll come back to uh, this again, right? So in this case, this is a figure that we looked at, previously a few minutes ago. And so in this case, we know that some of the energy has to be diverted to an array of detectors for the purpose of tracking, right? So 1 minus alpha fraction of the total energy is reserved for tracking, and then and the rest, which is alpha times the total received energy, is used for symbol detection, right? So what we can do is, in this case, what we can either reserve, we can divide this total energy in term as a function of time, right? So let's say we send pilot symbols first for tracking, and then follow that up with data symbols, right? Or what we can alternatively we can divide this energy in space, right? So let's say you transmit only data symbols, right? And then you separate the energy of the data symbols between this beam, this tracking channel and the symbol detection channel, right? And so the idea is that this power has to be allocated or divided optimally, in the sense that if too much energy goes into this tracking channel, right, then the energy in the symbol detection channel will be minimal, right, and your symbol detection performance will degrade, right? However, if you allocate too much power in the symbol detection channel, right, then the energy for tracking is minimal, right? And so your tracking performance will suffer, which will lead to a low SNR in the detection channel itself, right? Because if the beam is not aligned, right, then you do not get the maximum signal from the beam, right? So let's say if there's beam deviation, then only a fraction of the energy makes it to the receiver, right? So in order to maximize the energy going into the telescope, right, we need to be perfectly aligned, right? So again, I'll repeat myself. So if too much energy goes into the tracking channel, then you're not left with much energy for symbol detection. So this will increase your error probability. If you deviate too much energy into the symbol detection channel, then your tracking performance will suffer, which will cause misalignment, which will lead to low SNR at the receiver and a higher probability of error, right? So there's a sweet spot, there's an optimal value of alpha at which you will end up minimizing the error probability. So we looked at, we derived, expressions for the error probability. So those are derived in detail in the paper mentioned before, right? So in this block, we're using a centroid estimator for tracking, right? So we'll compute a centroid. It's a simple algorithm that computes the center of gravity of all the outputs of the detectors in the array, right? And based on that, this algorithm infers where the spot position is, and based on that we can infer the angle of arrival, right? So based on that simple centroid algorithm, we computed the optimal value of alpha, right? So again, here these plots show you the relationship between the bit error rate or the error probability as a function of this power division or power allocation factor alpha. So this is computed for the exponentiated viable feeding model, right? So we have two parameters there. So the red curve shows the best case scenario where your SNR is pretty high, right? And the blue curve is for very low SNR, right? So in both scenarios, and so on this side we see the error probability curves for the log normal fitting model, right? So in both scenarios, we see that, as if your SNR is high, which is, the red curve, right? Your alpha is also high. So alpha is the amount of power that's going into the symbol detection channel, right? Or 1 minus alpha is in the tracking channel. So if the SNR is high, your alpha is also high. So this means that you're diverting most of the power into the data detection channel, right? And as the channel degrades, you end up allocating more power to the tracking channel. So this was one of the findings that we got from this study, right? So again, this is true for most fading models that we studied. So this behavior is also reflected for this set of curves in this figure as well. So now we move on to the next topic on array, this beam tracking with arrays. So we'll look at this decision aided beam tracking system. So in this case, the idea is that you instead of sending separate symbols for tracking, or instead of diverting this energy, right? So let's look at this block first, right? This block diagram. Here. Here again, we know that we have a beam splitter that will divide energy between tracking and detection channels. So what about the fact that can we get rid of this assembly and use a single array that's used simultaneously for beam tracking as well as symbol detection, right? So this is a joint symbol detection beam tracking concept or model, right? So in this case, there's no being power division, right, between different channels. We have only one channel, and that's used for both symbol detection and beam tracking, right? So in this case, we can come up with a sensor fusion or data fusion algorithm, which is either an equal gain combining system or a maximal ratio combining system, right? So the idea is that you take all the outputs of each of these elements in the array and combine those in either in the EGC fashion or the MRC fashion, right? And then you send this back to the beam position, to this beam tracking assembly, right? So we'll look at this feedback channel, right? So the idea is that this array is providing data for symbol detection, and this array is also providing the same data for beam tracking, right? And so in this case, right, if you have this block, this data fusion block, right, you can connect this data fusion output or this this block to the tracking assembly as well, right? So so this will lead to a decision-aided beam tracking scenario, right? So we'll look at this, in the next slide, right? So the idea is that if you are sending these data symbols based on pulse position modulation. So in this case, let's say you have an 8 ppm scheme, right? So in 8 ppm, you have 8 slots. But you only transmit data in one of the slots, right? So let's say you're trying to send symbol 1. So this is symbol 0. This this location is for symbol 0. This is for symbol 1, symbol 2, symbol 3, and so on, right? So you have 8 symbols in your 8 ppm scheme, starting from symbol 0 to symbol 7, for example, right? And you transmit symbol 1. So to transmit symbol 1, you'll send the pulse in the second slot, right? And so the job of the receiver is to detect the light pulse in each of these slots to figure out which symbol was sent by the transmitter, right? And so based on this, you can decode what symbol was transmitted. And so this is a very common, non-coherent scheme for signaling in optical, in free space optics systems. And so in this case, you can so the idea is that, you can use this symbol for detecting the symbol. You can use the 88 ppm or any ppm scheme for symbol transmission as well as for beam tracking, right? So in the simplest possible scheme, of course, when you're not using decision-aided scheme, you're using pilot symbols, right? So in that case, you can that's the simplest possible system that we have, right? But if you use the a decision-aided scheme, right? So then you use the energy in your received symbols for tracking, right? So when you use the energy in the ppm symbol for tracking, you have two options. So first option is that you use the entire symbol period. So in this case, this is an example of an 8 ppm scheme. So your symbol period starts from time 0 until the slot 8 in this case, right? So you can either use the entire symbol period starting from this point to this point as your observation intervals, right? So in this case, you have some signal power, right? And then mostly you have noise power, right? So in most slots, again, 7 slots will have noise and only 1 slot will have signal in it, right? So in this case, you can use this interval and that the signal is present in one of these slots, right? And you can base your tracking, your algorithm, your estimation algorithm based on this observation, right? Another alternative is that you only look at the slot, right? So in the previous case, you have signal power in the observation interval. Let's say if you look at an entire symbol, of course, you have the signal power, which is due to this one signal, this one pulse, right? But you also have noise. So you have noise in 7 slots and symbol only in 1 slot, right? But if you consider the just 1 slot as your observation interval, which is actually the decision-aided scheme, right? Then you, of course, you will have noise from only 1 slot instead of multiple or 7 slots from the previous case, right? So in this scenario, if you use the slot as your observation, a ppm slot, then you end up minimizing noise, right? And end up maximizing the signal to noise ratio for your tracking algorithm. But the problem is that now you have to you depend on the error performance of your receiver, right? So let's say if the receiver begins to make too many mistakes, right, or too many errors, then you'll be looking at at the wrong slot for your tracking, right? So if the receiver is doing a good job, if the bit error rate is good, then of course you're sending the right slot or the right observations to your tracking, which contains the signal as well as noise. But if the receiver begins to make mistakes, then you're sending noise only observations to your tracking system, right? So that will hurt the performance of your tracking algorithm, right? So there's a dependence between the tracking performance and the bit error rate of your receiver in this scenario, right? And so if we look at this figure, so this is for the equal gain combining receiver, right? So we didn't look at the MRC because a bit more complicated. So we looked at the EGC, the equal gain combining receiver, right? So here we have 3 scenarios. One is that you use pilot symbols, right? And so we look at 2 options for each case. One is for an array of 16 elements. The other one is for an array of 64 elements, right? And for the simplest possible or the best performance comes from the pilot scheme, of course, right? Because you have dedicated energy for pilot symbols that's used for tracking. And then you have the 2 scenarios where, in one case you have observations from just a slot, right? And in the second case, you have observations only, from the entire symbol, right? So the red and the green curves correspond to the observations from entire symbol, right? And so, and the orange and the blue curves correspond to the performance from the slot observations, right? So here we're computing the CRLB, we're plotting the CRLB as a function of the number of noise photons in our system, right? So we see that for a higher SNR system, right, where you have more signal photons compared to the noise photons, the observations based on the slots, are doing quite well, right, as far as the tracking performance goes. But as soon as as the number of noise photons grows or the signal to noise ratio degrades, right, then the system based on the slot begins to suffer compared to the system based on the symbol observations, right? So there's a trade-off, right? So for systems with good SNR, right, which have high SNR, the system based on slot observations performs quite well. Of course, that makes sense because when you have high SNR, the receiver is doing a good job in terms of its bit error rate. And so, you're making the right decision most of the time, and that's helping your tracking channel or your tracking assembly. But if if the signal to noise ratio degrades, your bit error rate will take a hit, right? And so the receiver will end up making many more errors, and your tracking performance will degrade. So as the SNR degrades, the performance, the CRLB of the system based on the slot observations begins to perform poorly compared to the system based on only symbol observations. Right? So I mean, these are some of the guidelines, right? So for low noise power or for high SNR systems, we should base our decisions on slots. We can do that, right? Because it will give us better performance. And for high noise power, we should choose the entire symbol as our observation interval. So in this next set of slides, right? So we'll look at the effect of narrow Gaussian beams on the angle of arrival tracking or estimation of FSO platforms, which are mobile, which are moving, right? So this was presented this year, published this year in Transaction of Narrow Space. So the idea is simple in this case. The idea is that if the beam is narrow, right? If the beam width is narrow and you capture that energy and focus that on the focal plane of the system of the receiver, right? Then if you are at the center of the, if you're perfectly aligned, then for a Gaussian beam, you get the maximum energy, right? But as the angle increases or there's deviation, then the energy is not maximum, right? So the energy of the spot will also begin to decrease as you move away from the center of the array. So typically what happens is, in most state-of-the-art systems, it's only the spot location that's used for inferring the angle of arrival, right? So, and typically people ignore, the effect of symbol energy on the angle of arrival. The effect of the angle of arrival on the symbol energy or the spot energy, right? So for narrow beams, for wider beams, it's true. Even for large angles or large deviations, the energy in the spot does not change that much from the over the entire array. But for very narrow beams, if you are at the center of the array or if you're perfectly lined, right, then you get maximum energy. But if you move far away or if the angle increases, right, then the energy will also decrease. So you can use this information to track the beam, to track the angle of arrival of the beam, right? Because now the angle of the arrival of the beam is determining both the spot location as well as the spot energy, right? So you should be able to use the spot energy and build that into your Kramer or lower bound to estimate the angle of arrival more accurately. So just to give you an example, right? So in this case, if you're at perfectly lined, you're looking at the maximum value for a Gaussian beam, right? But if you have a certain angle and the angle is quite large, then of course, the Gaussian beam falls off with the angle, right? And so you don't get the maximum energy. So, and this is especially true for very narrow beams. If the Gaussian beam width is too wide or quite wide, then of course you don't see much degradation or much reduction in the energy, right? So these two figures highlight that. So in this figure, we see that, of course, if you're aligned perfectly, the angle of arrival is, the difference or the deviation is 0. But here there's a non-zero deviation, and also because you're at a certain angle, you're not getting full energy, right? So again, this shows you, the sort of illustrates, the energy in the spot as a function of the angle. Right. So of course, as at angle 0, when you're perfectly lined, the spot is brighter, right? But as you move away from the center, right, at this angle, then of course the spot begins to get dim, right? So there's a relationship between the energy in the Gaussian beam and the angle of deviation or the angle of arrival, right? So this is sort of captured in this figure on the right side, where the Gaussian beam is shown to have a Gaussian. Of course, this will be Gaussian as a function of distance, right? But in terms of angle, this is not a Gaussian curve anymore, right? So this looks like something else, but anything but not a Gaussian. So again, so this is the signal profile as a function of the angle, right? Not the distance. If you're looking at a distance, you'll get a Gaussian curve, but as a function of the angle, it's not purely Gaussian. It's the argument contains this Lambert W function, right? So this is the energy that's captured by the receiver, right? So A is the area of the telescope, and you can call this the aperture, right? And so once this energy is captured, this will be projected on to the focal plane array, right? So this is the profile on the focal plane, right? This is the spot profile. And so based on this, you can compute the fish information of the angle, right? So because the end goal is to measure the angle of arrival, and if you know the angle of arrival, you can always tilt the receiver in the direction of the angle of arrival to maximize the signal, maximize the received signal energy, right? So this is the fish information for the case when you have Gaussian noise in your receiver, right? So we have three factors here. If you look at this figure, right, at this equation 3, we see that this red number is based on only spot location, right? And so if you are not taking into account spot energy, right, then you're only left with this number, right? And so this is typically what typical receivers do, right? So they only look at spot energy, spot location, right? And so they have this as their fish information. But if you include the spot energy, then you have additional two terms, right? That you will end up adding into your fish information, right? And so the fish information is something you want to enhance or increase, because the inverse of this is going to be the CRLB or the Kramer-Rao lower bound, right? So we have something to gain if we are including the spot energy into our consideration, right? Otherwise, we'll end up missing these two terms, and we will not be maximizing the fish information. So again, the final slide is that this is the fish information as a function of the angle, right? But the major results come here. In this case, we note that so these four curves correspond to two types of beams. One beam has a beam width of 0.1 milliradians. The other one has a beam width of 0.25 milliradians, right? So the orange curve shows us the CRLB when you take into account the spot energy into the equation, right? Or you include both spot location and spot energy into your CRLB. And the blue curve here shows us the case when you only have spot location, right? So we note that, of course, the CRLB is minimized if you take into account the spot energy in your CRLB, in your equations, right? And of course, in the other curve also, we note that it's the same trend, right? So the Kramer-Rao lower bound is always minimized when you take into account or when you include spot energy, right, in your equations. So of course, in these two curves, the green and the red one, right, it's a wider beam, right? Of course, the Kramer-Rao lower bound is lower for the narrower beam, but sort of gets worse as you increase the angle or as you increase the deviation, right? So a narrower beam is helpful if your deviation is small, right? So then you can track the beam more accurately. But a wider beam is more advantageous if the deviation is large, right? Because of course the narrow beam will have very small and very little energy, right, if the deviation is large, right? So there's always a trade-off, right, that which beam width you want to choose. So looking at these figures, we note that one guideline was that for a slow-moving terminal, right, or if or for a system that updates theta very quickly, right, the deviation will not be very large from one instant to the next, right? So you can rely on a narrower beam in that case, and improve your tracking performance. But for a system, for a terminal that's moving very quickly or very fast, right, or if your or the rate at which you update your theta is low, right? So in that scenario, you need to transmit a wider beam, because a slower update of theta or a fast-moving terminal will lead to a higher beam width deviation, or higher angle deviation, which will be difficult to track, right? So in that sense, you need to transmit a wider beam in order to estimate the angle of arrival. Slim, do you want to continue on this one?
Yes.
Right.
So let's now go back to a fundamental topic on FSO systems and look at how to select optimally the detector size. So this is actually quite recent result. Salman initiated this work, and the paper I think just appeared on early to access in transaction wireless. So let me try to kind of explain the problem. So maybe you can go to the next slide. So the idea here is, when you think about it, we are talking about one of the main issue that limits performance of FSO system is basically the size of the pointing error. So one may argue, why not make the detector size as big as possible, right? The point is that actually when you make the detector size very big, within the area of the very big, you make at the end of the day is like an RC circuit. You make the capacity very large, and you limit the bandwidth. So in other words, the way the problem can be viewed is that the average collected power is proportional to the area square, whereas the bandwidth is inversely proportional to the area of the full detector. So let's take as a potential metric, and we can look at other metric like bit rate and capacity is another metric we looked at in this context. Basically, the capacity is written in this expression. And as you see, in the capacity, the power appears here, the numerator. The bandwidth appears both here and here. And as I mentioned, the power is proportional to A squared, whereas the bandwidth is proportional to 1 over A. So if you plot the capacity as function of the area, so if you look at just capacity per channel use, like the orange kind of part of the formula, it's of course increasing as function of the area, because it's just basically proportional to log of A, pretty much. Whereas the bandwidth itself is inverse proportional to A. So when you combine W, the blue kind of part of the equation, and the orange part of the equations, the blue and the orange, you get this green curve, which is the capacity in bit per second. So and as you see, there is, of course, clearly an optimal size of the detector. Actually, when Salman kind of presented these results to me the first time, I was surprised that this fundamental problem has not been kind of discussed earlier, because it seems very basic kind of formulation. To our best knowledge, although there was a very recent, pretty much simultaneous experimental paper discussing this issue, published at a conference in Netherlands roughly at the same time, there was no really analytical study to analyze this optimization of the for detector size. So next slide for Salman. So if you want to dig further into this, so basically this is kind of a modeling of the photo circuit detector. As I mentioned, it's an RC circuit. You can relate basically some of the parameters to the resistance and the capacitance that constitute the circuits. And here, this is the kind of intensity mu0, the noise power, and you can define these parameters. So next slides.
Yes.
So what matters here is when you go back to the yes, please, next slide. The capacity formula we talked about earlier, and you substitute the parameter that we just introduced and isolate or kind of identify the dependence on A, which is the area of the detector. You end up with this expression where the capacity is this alpha over A log 2 log 1 plus this parameter defined earlier, A cube. Okay, so the SNR is basically this factor. You can call this normalized SNR, and the whole idea is to identify this optimal A. I mean, it's very simple. The way you can get it is by taking the derivative with respect to C, with respect to A, equating that to 0. You have to solve this transcendental equation. it turns out that A can be written in terms of a Lambert function, and that's a closed form expression for the optimal size that Salman was able to derive as function of the system parameter gamma naught, and B is basically this kind of constant which is expressed in terms of the Lambert function, and alpha and beta naught were the parameter depending on the model that was presented in the previous slides. So that's kind of in a context of a clear free space optic link. In general, a free space optic link can be subject to turbulence, can be subject to pointing error. So the idea was how to optimize the size of the detector in presence of these kind of turbulence or misalignment. So the next part of the paper was about that. So next slide, Salman. So obviously, I mean, if you want to do it optimally, you'll have to kind of optimize the average capacity. It's difficult to obtain in closed form. So as a suboptimal solution, here what was proposed in the paper was to take the solution that was optimal for a kind of a snapshot and replace it for every single realization, and then average over. So that was the optimal solution identified for a snapshot situation, and then replace the fact that now beta is not constant, is a function of this R, but then you average over R and you obtain this A star, which is again not optimal, it's suboptimal, but it's the approximation of the optimal solution. The good thing is that it can be obtained in closed form. Same thing, this is under pointing error. Assuming a Rayleigh pointing error. If you assume an negative exponential turbulence, you can do the same thing and on a snapshot based get the previous result, average over the turbulence that is modeled by an exponential distribution, and this anti can be solved in closed form, and you get at the end a closed form expression for the suboptimal detector area. Now, if you look at the plots, you see that next slide. Here, that's optical detector area for a kind of fixed SNR ideal type of situation. Indeed, as of course the intensity increases, your capacity increase, and clearly you have always this optimal value that we are able to determine in closed form exactly. Now, in the case of pointing error or in the case of atmospheric turbulence, our proposed suboptimal solution come very close to the optimal solution that cannot be obtained in closed form, but not that far. But again, you have the same kind of behavior. Of course, the stronger is the pointing error. Here, for example, a very small pointing error gives you a very high capacity. It's like nearly like ideal case, whereas a strong pointing error, you end up having a loss in capacity. Same thing here. This is a parameter that controls the intensity of the turbulence, and the stronger is turbulence when eta is 0.8, is 0.2, like is small here, you get a lower capacity. As you see here, the approximation in the case of atmosphere is not as good. It is not far, but it's not as good as basically in the case of pointing error. Next slide.
Right.
This also, the paper includes actually extension to multi, let's say, full detector, array of the detector, and again, is available on early access. Let me give back now the floor to Salman to talk about this relaying UAV type of scenario.
Right. Thank you, Professor Slim. So this was presented in 2022 in a journal. And so the idea was that, we have this optical link, this laser link, right, that's has a certain length, right? So this extends to quite a few kilometers, right? Or, even, could be extended to hundreds of, or, even thousands of kilometers, right? So the idea is that, you want to introduce relays because, of course, if the link is too large, or if the level of turbulence is too large, right, then the signal reaching the receiver would be quite weak, right? So in that scenario, it's important to introduce relays at the intermediate points within the link, right? So for traditional FSO systems, of course, we know that the most commonly used set of tunable parameters are the beam width, the receiver field of view, right? The detector size, power split factors, for example, between beam tracking and simple detection channels, right? So all these parameters can be tuned to maximize a certain quality of service metric or minimize bit error rate, for example, right? However, if you have aerial platforms, right, so then these platforms are flexible in the sense that they can be moved about quite easily, right? So we have more degrees of freedom in terms of their flexible movement, in terms of their flexible positions. So depending on the channel behavior, right, we can adjust the positions of these relays to maximize a certain metric. For example, it could be the minimization of the error probability or the minimization of the outage probability, right? Again, we can use different types of relays for these aerial platforms. We can use either the amplified forward relay, which is sort of the simple relaying system that just takes the signal and amplifies it and then retransmits the same symbol without taking any action on the noise, right? Or we can use a decode and forward relay, which is a more sophisticated relay in the sense that this relay will take the signal, receive the signal, decode the symbol, and then transmit a new copy of the symbol, right? So this relay is more complicated. So in this paper, we looked at only the AF relay or the amplified forward relay. So the problem is that you have a certain source, which is again a UAV, right, and a certain destination, and you want to transmit the signal, the laser signal, from the source to the destination, but the link distance is too large, or there's turbulence, so you want to introduce relays, intermediate relays, right, to minimize the effect of this harsh channel condition. So one question was, so how do we choose the positions of these intermediate relays so that we can minimize the outage probability, right? So in this case, we are using, again, like I said, we're using amplified and forward relays, right? So we looked at the problem, and then we realized that if you have a channel that's dominated mainly by the pointing error, the Rayleigh modeled pointing error, then you can get closed form expressions for this particular problem. So this can find applications in, let's say, in the stratosphere, where there's minimal turbulence, but there is significant pointing error, right? Or even in space, where there's no turbulence, and of course most signals in space, optical signals in space, suffer from pointing error. So this can find applications, especially in space or in the stratosphere, where you have where you can place platforms like HAPs, right, or high altitude platforms. So this study will apply in that scenario, or in terrestrial systems that have minimal turbulence and significant pointing error. So in this case, so this is the definition of the pointing error. So the idea is that there's these two platforms, right, they need to be aligned, right, in terms of the angle, so that the receiver can receive maximum energy, right? However, if there's some certain pointing error, for example, in this case, phi, this angle is the pointing error. So if this is 0, then the two platforms are perfectly aligned, right, and the receiver will get maximum energy, right? However, if phi is not 0, which is the pointing error, then this receiver will be at a disadvantage, in the sense that this will not receive maximum energy, right? So the pointing error is something that will cause signal degradation or cause signal fading. So the simplest possible model for pointing error is based on the Rayleigh distribution. So this is true when you have Gaussian deviation in either x-axis, in both x-axis and y-axis, and their standard deviations are also equal, right? So zero mean Gaussian distributions along x and y-axis independent with similar standard deviations. So that will lead to Rayleigh distribution for the pointing error. And so we derived this, so for a channel mainly affected by pointing error, this is what the channel distribution looks like, right? So phi is a constant, which is a normalization constant, and B in this case is this number, which is based on or depends on the area of the aperture and the beam width and the link distance, right? So of course, and 1 is the indicator function here, the function that's 1 when the h value is within this interval from 0 to b. So So again, when we solve this problem, so we based the solution on the Lagrange multipliers, right? And so with a channel that's mainly affected by Poynting error, that's really distributed, we were able to obtain this expression for the AF relay case. So the optimal solution is given by this expression. So theta is the angular beam width, and sigma is the angular Poynting error standard deviation, right? Sigma squared would be the Poynting error variance in this case, right? So this factor determines the optimal location factors, right? So D is the total link distance from the source to the destination, right? And then ZM being the interlinked distances, right? So ZM C0 would be the link distance from the source to the first relay, and Z1 will be the interlink distance from relay 0 to relay 1, right? And so on and so forth. So we can find out the optimal positions based on this expression. And so one thing we found out, of course, that these interlinked distances, they form an increasing sequence, right? So that's one thing. And the second thing was that if you have a perfect channel where there's no Poynting error, right? So in that case, this collapses to uniformly distributed interlinked distances, right? And so again, if sigma is too large, of course, then you'll have non-uniform distribution. So as sigma increases, more and more relays will become closer to the source, right? Because this is an AF scheme, so the error accumulates because this system is not regenerating the signal, right? So it's accumulating error. So the idea is that you want to be, if the channel is quite bad, most of the relays will be closer to the source, so that you don't accumulate too much error while going from the source to the destination. So you sort of, this spacing becomes more and more non-uniform as sigma increases in relation to theta. Sigma being of course, the Poynting error standard deviation, theta being the beam width of your laser signal, right? So this was one example. Here we'll look at some typical values. So typical plots, right? So again, this is the outage probability. So we computed the outage probability as a function of the beam width in this figure, right? And so we looked at the effect of the number of relays in the link, right? So the plots that are shown by solid lines, so these are determined based on uniform spacing of these UAV relays, right? And the dashed ones show us the results for optimal positioning, right? So for these parameters, we computed these curves, right? So for this particular set of parameters, we can see that the improvement is significant in terms of the outage probability compared to the non-optimized case or the uniformly distributed case. Similarly, we plot this outage probability as a function of the gain of the AF relays, the amplifier and forward relays. So we have this trend. And so Professor Slim, do you want to? Sorry.
Yes. So let me follow up with this kind of interesting problem where here we emphasize the kind of dual use that the laser can have. Actually, you'll see later on that it has actually even other uses, like in terms of localization. But here we are trying to emphasize that the laser can be used to transfer information, but also transfer power. This is critical in the context of non-terrestrial network. So yes, can you move forward? So here, as kind of a scenario of interest, I mean, it doesn't have to be exactly like this, but that's what was presented in this paper. Let's assume you have kind of a way to generate power in a very, let's say, green fashion, like you have hydropower or solar panels in a particular location, and you want to transfer this power to basically like in a particular destination. So and you have also information, let's say, that you want to transmit simultaneously to that. So here you have a tether UAV in the way. This tether UAV is basically transmitting this laser beam to power this UAV. You want this UAV to kind of be aloft as long as possible. You know, one of the main problems of UAVs is kind of they have a limited battery lifetime. So this laser power mechanism will allow this UAV to stay aloft for kind of a relatively long time. So basically, yeah, this laser beam is being used to power this UAV and also to transmit information to this receiver. So we have here what we call channel 0 is the source to the relay, and channel 1 is relay to destination. The total distance is D. Z is the length of source relay. D minus Z is remaining length. Okay, next slide. So, okay, here obviously you account for pointing error using what we call Rayleigh type of pointing error, which means you assume that you have vibration that are Gaussian in the, let's say, horizontal domain and also Gaussian in the vertical domain. So, you know, as amplitude, you get the Rayleigh distribution. The square of that gives you an exponential. And when you do transformation, you get this distribution of the channel H1. And then for H0, same thing. You have the other kind of pointing error. So you have typically the same distribution. Next slide. So now here is this kind of trade-off where you kind of, in a way, has to manage this laser beam that is being used to simultaneously transmit information and power. So we have a fraction of power, let's say delta, that's being used for communication, and 1 minus delta is being used for power transfer. And the question, what is the optimal delta? So obviously, I hope you all realize that there is kind of a nice sweet spot here for picking the right delta, because if you put too much power on the transfer of energy to make the system fly and stay aloft, then yes, it will be aloft, but will not have enough SNR to transmit information reliably. On the other hand, if you can put too much power on, let's say, the biggest power, the fraction of power to information transfer, yes, you can transfer information reliably, but it will be over a very short time because the drone will not have enough power to stay aloft. And that the idea was to find the right delta, the right kind of way to split power between energy transfer and information transfer. Yeah. So this is very easy. When you have a two-hop type of system, assuming decoded forward, the end-to-end capacity is kind of constrained by the bottleneck of the tooling, so like the minimum capacity of the tooling, and that's what we have here. So it's the minimum of the first capacity, which is function only of the first link, because that's on the first hop, and the second capacity of the second hop, which is function of the first and second hop. So obviously C0, H0 is just like your standard channel capacity, where delta here is the power allocated for the first hop, and then that's kind of 1 minus delta allocated to the second hop here, and then obviously that's the final formula for the overall capacity. So the capacity here is given by this averaging over the two channel distribution, assuming this minimum, and you see it's all functional delta. So I mean that's basically the problem formulation. You want to find the optimal delta, you just take capacity, you plot it, and you try to find the delta that maximizes capacity. But what Salman did in the paper, he tried to kind of come up with different approximations, try to find some closed form expression in different regimes. But in the slides, we are just showing some plots, showing exact results, showing this optimal delta as function of different value of the distance of the first hop, second hop, different kind of beam width, let's say opening for the theta 1, the first hop, and here is the guideline that the source relay distance increase, the optimal delta will increase to improve source relay performance. Beam width and relay destination improves, the optimal delta will increase to improve the performance of source relay. So again, and yeah, here actually the delta is like how much fraction you give between the first and second hop. So, and you know, there is this interesting kind of optimal value. Next slide.
Yes.
Yeah. Yeah, so now this is another interesting aspect where we are using also a laser, an FSO, not only for communication, but for localization. So this is a recent paper done by our PhD students, Yu, co-supervised by myself and Professor Salman. So the motivation, let's go to the next slide. Is basically when you are in a GPS restricted environment, there is spoofing, jamming, you know, like essentially you are not able to acquire accurate GPS locations for drones, HAPs. The idea is to rely on a laser link using LiDAR technology. So LiDAR is like a in a way a radar, but it's using an FSO link to kind of shine on a particular area and to get an echo, and then with that localize some kind of targets. So the idea here is to use a LiDAR to try to localize drones, but then beyond localizing the drone, we want to take advantage of this system to completely lock onto the full detector and establish the FSO link. So it's a joint localization and communication system using LiDAR / FSO. And you want to have this fine acquisition so the FSO start transmitting reliably information through this link. And you want to, of course, as I mentioned earlier, to minimize this total acquisition time. So next slide. So the mechanism that we are talking about here, so yes, you have an energy source, you have an energy splitter. Fraction of the energy is going to be allocated to LiDAR function, and the other fraction is going to be allocated to the FSO transmission. You have, like in any kind of static mechanism, an optimal value. If you put too much on LiDAR, you have accurate kind of estimation, but not enough transmission communication, and vice versa. So the idea was to try to find the optimal also alpha to kind of optimize the joint function of this system. And our utility or objective function here was to minimize the average acquisition time or maximize CDF of the acquisition time, the probability that you make sure that the acquisition time is below a certain desired threshold. Next slide. So this is basically the way. Maybe we can describe this algorithm in the next figure, please.
Yes.
So the idea here is you start by having a certain a priori knowledge of the uncertainty sphere where the drone is located, and then you start basically firing. So this initial, of course, is based on the LiDAR given initial estimate of the UAV coordinate U0, V0, and then the FSO acquisition transmitter search within this region by sending a maximum of N0 pulses. Okay, trying to basically lock into the full detector. Okay, now if it happens that within this N0 you are able to lock, you are done, and you start your transmission. But it may happen after N0 you still didn't lock because you missed the detect, like the full detector, or you were not able to hit it. So basically you reuse again another LiDAR shot to try to re-estimate the location of the drone, and then repeat the same process by doing up to N0 shots of FSO acquisition transmitter to be able to locate the exact full detector. And you keep doing that, you know, as many times as needed to basically lock into your full detector. So mathematically speaking, what we have here, yes, next slide, please, Salman. So your total time is the X attempts you tried and you were not able to kind of lock. So X times T1. So X again is a geometric random variable, and then basically the total acquisition time is you have basically. So T1 here is the time for one course acquisition attempt, which is the LiDAR. You need to have X times LiDAR to kind of to every time you fail with the LiDAR to lock, you try again. So, and you assume at the X time you kind of you acquire the signal. So X is as a last attempt, and again it's like the geometric random variable. Now in this in the X minus 1 failed attempts, you use N0 shots, and for every shot you have a T2, which is the time needed for one-time acquisition attempt with FSO. In the last X basically attempt, you are successful. You don't need to use N0 FSO shots, acquisition shots. You use only N times T2. So the bottom line, what you end up having here is, if you look carefully, you have basically a weighted sum of a classical geometric random variable X and another, let's call it a truncated, actually it's written here, truncated geometric random variable N, because the number of FSO shots you allow yourself to use are up to N0. So it's a truncated N0 in the sense that it stops at N0. So the bottom line here is that your acquisition time is this weighted sum of classical geometric random variable and a truncated geometric random variable. With basic probability, one can derive the probability mass function of this combination of these two geometric random variables that is given in this formula. Next slide. And with that, you can derive the basically expected value of the number of attempts as function of the probability of Pn here is like function of the beam coverage probability and the probability of detection probability given there is a beam coverage. Next slide.
Yes.
Yeah. And then once you have this characterization of the random variables, you can get the T as a, again, weighted sum of these two geometric random variables, T1 plus, and the average value is given in this closed form expression, and you can even get the CDF again as function of the same parameters. So it's an exact full characterization statistically of the mean acquisition time and the CDF acquisition time, and within that you have, of course, the embedded alpha parameter that you are trying to optimize. So for instance, in the next slide, you will plot this expected average time as function of this alpha parameter for a variety of noise levels. And as you see here, there is this nice spot for every single value of alpha, for every single value of the noise level for which the expected value is minimized. And similarly, there is a nice maximum for the CDF of the acquisition time for alpha for different noise. So that's really the main kind of objective of the study. And I'll give back now the floor to Salman for the follow-up study before we wrap up this tutorial.
Okay, thank you, Professor Slim. So this is the final set of slides on this topic for this tutorial, right? So the idea was that so again in this problem we didn't look at the the communications perspective. And so the main idea was that we want to maximize the laser power transfer to a fixed wing UAV, right, which is flying through turbulent atmosphere. So the criterion in this paper was to maximize the laser power, right, without looking into the communications aspect. So this was more of a a problem along the lines of power transmission or power maximization. So in this case, I mean, of course, we know that as Professor Slim mentioned that the UAVs are constrained in energy, so they carry batteries or fuel, right, and so they cannot fly indefinitely. And so if you want to maximize their flight time, or you do not want the UAV to land first and then recharge and then fly up again, so in that scenario you can charge the UAV while it's still flying in the air, right? So an application could be that the UAV goes out to do its job, and then it comes back to the ground station or its base and flies over to get charged, right? So this could find applications in networks like disaster systems or special networks where you are where there's perhaps there's no landing base for the UAV, or you cannot it cannot land as many times as you would like it. So you want to charge the UAV while it's still flying in the air. So so in this case, so this figure is showing us, that there's a ground charging station that's firing laser at this UAV to charge it, right? So again, in experiments, so this is again not science fiction in the sense that there are actually organizations, companies that are working on transferring huge amounts of power to different platforms, right? So in recent experiments, it's been shown that you can transmit up to 1 kilowatt of power up to a distance of 1 kilometer. So this technology is getting more mature over time. So in order to pose the optimization problem, so again in this case, the UAV flying a fixed wing UAV, when it's flying, it consumes energy according to this model, right? So again, this is the energy consumption model of this UAV. So the power consumption depends on two parameters. One is the mean velocity, which is mu sub v in this equation, and the other one is the radius of trajectory. So let's assume that the UAV is flying in a circular sort of trajectory, a circular path to get charged by this ground station, right? So in this case, if the UAV follows a circular trajectory, then the power consumption of the UAV in that circular path is given by this expression. So C1 and C2, these are some constants, right? And the main thing here is that the power consumption formula it's convex in the mean velocity mu v of the UAV, right? And this is in terms of R, this is monotonically decreasing in terms of R, right? So again, the main goal of this paper was that a UAV that's flying in turbulent air, right, and a UAV flying in a circular trajectory around the ground charging station, how can we choose the optimal trajectory radius and the optimal mean velocity that will maximize the net laser transfer or net power transfer to the UAV, especially in a turbulent air environment. So again, the goal is to maximize the net received power or the net power, right? So this is going to be the difference of the received power, right, and the consumed power, right? So these two powers, the received power and the consumed power, they both depend on the mean velocity and the trajectory radius, right? So if you plot the consumed power as a function of mean velocity, then of course there is a convex curve, right? And so it attains a minimum velocity at mu v star, right? And of course we'll show. So we showed in the study for later that the received power decreases monotonically with respect to the mean velocity. And so in this case, the difference of these two will look like a concave function, right? And it's the peak value of this net power will be, which is represented by mu v asterisk, right, will always be less than the mu v star, which is the power, which is the minimum power consumption velocity, right? So at mu v star, the consumed power is minimum, right? But at the mu v asterisk, which is the actual optimal velocity for net power, right, is always less than the power minimum velocity, the power consumption minimum velocity, right? So this is one thing that we learned from this figure. And so in terms of R, the power consumption is monotonically decreasing with respect to R. So in terms of the PC's dependence on mu v or the mean velocity is evident in the sense that if for a fixed wing UAV you cannot force the UAV to stop in mid-air, right? Because that will lead to extreme power consumption. So a velocity of 0 will lead to infinite consumed power for a fixed wing UAV, right? And so and of course if the UAV cannot exceed its maximum speed, otherwise it will again begin to consume maximum power. So there's a case to be made. There's a case we can make that for a fixed wing UAV, there's an optimal velocity at which the power is at which the consumed power is the minimum, right? So again, in terms of R, right? So if you shorten the radius of trajectory, then of course a fixed wing UAV has to turn about very quickly. So that will increase the consumed power. But if the UAV is allowed to move in a straight line, then its consumed power will be minimal, right? So these are evident. These curves, the consumed power curves, are evident from intuition as well as from the equation that was shown previously. So in our case, we showed that the received power is concave looking, in terms of R, right? And so the R asterisk, which shows which is the maximum of the the net power, right? So R star is the radius at which the received power is maximized, but R asterisk, which is greater than R star, is the radius at which the net power is maximized. So we showed that so we've discovered that the R asterisk, which is the ultimate optimal radius, is always greater than or equal to R star, which is the radius for which is the optimal radius for the received power, or the radius at which the received power is maximized. So here we looked at we formulated the problem in the context of a dynamical system, right? So the idea was that the velocity is changing randomly as a function of time. So n here is the discrete time index. And so we showed in the paper that this varies according to this formula, right? So un is this function which depends on this important factor delta rho. So delta rho n is the random change in the air density, which is modeled by Gaussian distribution. And so this was based on another paper there was submitted in NASA technical reports, and so we based our this argument on that paper. So delta rho, or the change in the air density in a turbulent environment, is modeled by a Gaussian distribution. And so CD, this factor, is the UAV drag coefficient, A being the cross-sectional area of the UAV, and M is the mass of the UAV, right? So this factor UN is based on all these parameters, and more importantly on the air density variation. So the turbulence actually is modeled into this factor delta rho, right? So if the level of turbulence is large, then the delta rho, the variance of delta rho will also be large, right? So the level of turbulence is captured in the variance of delta rho, or the change in air density. So UN is given by this number sigma u squared. So it can be computed based on the variance of delta rho, right? And WVN is the velocity measurement noise, right? So this is based on measurement of velocity with the LiDAR. So it was shown that of course the mean value of this velocity is at any time n is the mean velocity of the UAV, and the variance of this velocity is dependent on the fourth power of the mean velocity, right? So the important conclusion was that the variance of velocity was dependent on the mean velocity itself. So especially this is true only for a UAV flying in turbulent air. So again, the end goal was to, of course, when you're trying to track the UAV, because of course you want to maximize you want to transfer power to the UAV, or you want to transfer laser power to the UAV. So in that case, because the beam is quite thin, so you want to track the angle of the UAV, or the angle of arrival from the UAV, as accurately as possible, so that you can accurately point the beam to the UAV and maximize power transfer, right? So the idea was that in the end, you want to measure the angle theta of the UAV with respect to with respect to a certain reference. And so this theta evolves in time according to another dynamical model, right? So again, all these other parameters are listed over here. So these are certain constant. Kn is the control input in this case, right? So the idea is that, okay, you want to make sure that the UAV always it follows a certain it lives within a certain range, right? So that's why you have control input that controls the velocity as well as the radius, right? So Kn is the control input. And so we have some, asymptotic expression. So the measurement of theta was based on a LiDAR. So you have a LiDAR at the same location, almost the same. So the LiDAR and the ground station, they are sort of co-located, or they are located at the same station. So you take all the measurements with the LiDAR, right? And then you try to accurately point the beam to the UAV, right? So the angle was measured with the LiDAR, right? So again, these are the equations of the measurement noise based on a photon counting receiver LiDAR, right? So a LiDAR that incorporates a photon counting receiver. So these are some different, this is the expression for the variance of the measurement noise. And so F is the focal length of the focal plane of the LiDAR receiver. And so P0 is the power, R is the distance, the trajectory radius, right? And H is the height of the UAV. And so these different parameters are, PET is the transmit power, G is the gain of the, the LiDAR antenna, and then of course AR is the LiDAR receive aperture, and then EP is the energy in a single photon computed at 1550 nanometers, and so on. And sigma, of course, is the cross-sectional area of the UAV. So, and then so the idea was, okay, you want to accurately track the UAV as accurately as possible, right? So we used a common filter to track the angle, and so this was the final expression that we got for the mean square error. So M is the mean square error, and infinity means that this is a steady state MSC, right? So this is this is not the transient MSC. This is steady state MSC. And so this is the factor that's based on this M value. This is based on the mean velocity and other parameters. Delta T is the update time of your LiDAR. So every time you send a pulse, that's based on delta T, the frequency of your LiDAR pulses. And so tau is the time difference between any two measurements of theta. So once we compute that, so again, this is the first set of curves that we obtained. So this is the mean square error of the angle of the UAV, and this is again measured with the common filter. So this is the common filter MSC of the UAV angle, and so as a function of the velocity, this is monotonically increasing. So this can be explained as follows: as the velocity increases, the variance in velocity will also increase, right? So this will lead to more random change in the angle, right? Because of course the angle itself depends on the velocity. So a larger velocity implies a larger variance in velocity, which implies a larger variance in angle, which is more difficult to track with so your mean square error will increase as you increase the mean velocity. In terms of R, the mean square error is a convex function, or a convex looking function. So the idea was that, okay, the mean square error, right? This is it's convex, right? So if this can be explained as follows: if R is too small, right, so then your UAV is flying in a very small radius, right? So the angle changes very quickly in that small radius, right? And so quickly changing angle is difficult to track with a common filter, or or with a combination of the common filter and a LiDAR. So your a small radius is not good if you want to improve your mean square error performance, right? So that's why your mean square error goes up if the radius is too small, because it's difficult to track a rapidly changing angle. And on the other hand, if your radius is too large, then of course the change in the angle per unit time is not that large, right? It's quite small. But now the problem is that your LiDAR loses SNR, right? So you have to transmit for the same energy, right? The return signal is very weak. So the measurement process suffers, and your mean square error goes up. So there's a trade-off in terms of where you should have your best radius to minimize the mean square error of your common filter. So this is some models that we used for the fading and the scintillation. So this is the gamma distribution that's that was used for modeling the scintillation of the optical signal. Right, so these are different parameters, and among them, we have this important parameter CN squared, but that depends on the refraction structure parameter of the environment of the air, right? And all these other parameters, lambda is the wavelength, is the receive aperture diameter, right? So gamma distribution is characterized by these two parameters A and B, right? So the values are shown here, the expressions, and so the received power, of course, at the LiDAR, at the UAV from the ground station, will depend on, of course, both scintillation and pointing error. So the scintillation part is captured by I, right? So I is a random variable that's modeled by, or that's driven by this gamma distribution, and the error part is the pointing error part is this epsilon, bold epsilon. That is the that's driven by the common filter error, right? So E depends on the performance of the common filter, right? And so again, here we're using the Lambert W function. So this is the received power as a function of scintillation in the channel as well as the pointing error here, right? So the average received power, you can compute that by averaging over the distributions of the common filter error and the gamma model for scintillation. So here, so we showed, we demonstrated, we didn't prove it, we demonstrated that, the common filter error is Gaussian, or is approximately Gaussian. So we used Gaussian distribution to model, FE. So again, this is the received power at the UAV, right? So again, if you intuitively, we can explain it, based on, if you look at, the MSE curves, right? So the received power curves look like the inverse of the MSE curves, right? So here, we know that, okay, as the velocity increases, the MSE will increase, right? So of course, your received power will decrease, right? Because, a large velocity will imply larger variance in velocity, which implies larger deviation in theta, which is, which minimizes the received power. And also, of course, in terms of R, of course, as for a small R, the angle is changing rapidly. It's difficult to track. The MSE goes up, and of course, your power loss, your received power, comes down, right? And if the R is too large, then of course, you are losing energy because of the large distance between the LiDAR. So you're not doing a very good job in terms of measuring the angle, because the UAV is too far away from the ground station. So you lose energy as force power for LiDAR, right? As a function of distance. So a large R implies that the LiDAR does a poor job, as well as the received signal also, the laser power from the ground station also minimizes because of this large distance effect, right? So we have, these curves that can be explained intuitively, the received laser power. And so in the end, we take the difference of the received laser power and the consumed power. And so we have these curves of the net power that the UAV obtains from the ground station, right? So both these curves, like, in terms of the mean velocity as well as for R, indicate that there's an optimal value at which you can maximize the net power that's transmitted or received by the UAV from the ground station. So then we plotted, so in the next final slide, plotted the optimal velocity as a function of this vector sigma rho squared. So this vector captures the level of turbulence in the air, right? So the larger the value of sigma rho squared, the larger the value of turbulence. And so we know that the optimal velocity decreases, right? So these are computed for different values of the transmitted power, right? And so the optimal velocity decreases as the air density or the air density variation or the turbulence goes up, right? So there's an inverse relationship between the two. And in terms of the optimal radius, the optimal trajectory radius, it's a direct relationship. So as the turbulence levels go up, the optimal radius also goes up. So based on these observations, we came up with these guidelines that will help to maximize net power to the UAV. So for when the air turbulence is large, the UAV should reduce its speed and increase the trajectory radius to maximize the net power transmitted to it. And for little to no turbulence, the UAV can operate at higher speeds and fly in a smaller trajectory radius to maximize net power. So these were the two main takeaway messages that we had from this study. So finally, I think this is the final slide. And
thank you, Salman. So I think I hope we gave you this kind of perspective on some of the new and emerging topic on FSO. We'll be happy to take some questions and also share with you the slides. I think the slides, you can email them to Luciano, and they can be available to the whole audience.
Okay, so do have time for some questions from the audience? Okay, you have one here.
Hi, my name is Luis Augusto, and thanks for the presentation. And the work with LiDAR, if I understand, the LiDAR is used for initial drone detection. And after that, since you also want to establish an FSO link communication, you perform the shotgun approach for detection.
Correct.
And I'm curious about why not using the method based on the spheres that you previously explained.
The spiral, you mean?
Yes.
Yeah. I mean, we could have used the spiral. We can use the kind of other type of kind of search approach. But I think for analytic tractability, and Salman, you may correct me if I'm wrong, because you're the kind of you work closely with AU on this. For analytic tractability, we just kind of use a shotgun approach to focus on this trade-off on how to allocate power between basically localization and acquisition. But I mean, the work can be, I guess, extended to look at more, let's say, sophisticated acquisition strategies in combination with LiDAR.
Okay, thank you.
Any other question? There is some questions from the online audience. We do have a question here from Christopher Runge. Thanks for the brilliant presentation. Do you have any information about OEM, orbital angular momentum, based the FSO in ground links?
Yeah. I mean, OEM is an approach to multiplex multiple, let's say, data stream over FSO. So it's like MIMO, but instead of doing it from multiple lasers, you are doing it basically with different patterns. You can do it this way. This comes at the expense of the fact that the beam gets wider and wider, like in contrast to a Gaussian beam, which is kind of relatively simple to generate and kind of detect. When you start multiplexing multiple beam, you can end up having larger and larger detection areas, and also you may have leakage. Like you think in theory, these in a way that you are creating orthogonal, let's say orthogonal modes in theory, but as they propagate through turbulent environment, you start having leaks between the different modes. So essentially, you start having crosstalks, and there is quite a bit of work on that. But I believe, I mean, that's my again. I have done some work on that, but this is not like at least these days our main focus. I think this may be a good way to increase capacity in situation where already you are very close to capacity, or like we are already kind of fully kind of squeezing the available bandwidth. That's the case now in fiber. Remember when we start with fiber a few decades ago, we were like in the FSO now, a lot of bandwidth, so on-off keying was good enough, pretty much 0 1s. But now fiber actually, because the terrestrial network that are kind of wired are more and more demanding, we're trying to squeeze more and more out of these fibers. And I think there we are trying to be more spectrally efficient. For FSO, getting more spectrally efficient will come at some point, but there is some research from OAM to do that. But I don't believe it's a pressing issue today, because I think we still have a lot of bandwidth to kind of capitalize on before we reach the time where, yes, we need to start to deploy OAM. But definitely is a good research topic.
Okay, wonderful. We do have time for the last question. I would have one question, Professor Slim, regarding the presentation for the outage probability, where you have multiple links using the drones. Which factor would be more impactful for the reliability of the link? The variation of the position of the device in the air, or the impact of the atmosphere in the laser beam?
I'll just give a general answer, and then I will let Salman maybe specifically answer for this particular question. In general, when you have a multi-hop link, the capacity, the outage, the bit rate is going always to be basically constrained by the weakest link. If there is one link, like you have L multi-hop, the capacity will be basically kind of limited by the bottleneck will be the worst link of all of them. Okay, so this can be because the link is misaligned, because the link is subject to more turbulence than other, because the link is too long compared to others. So whatever is the reason why that link is bad, the result is that link is going to dictate the performance of the end-to-end performance of multi-hop link. So that's my general answer to your question, but I will let maybe Salman give you maybe a more specific answer to the topic that he presented, where he optimized actually the location of the UAVs.
Yes, thank you, Professor Luciano. So it's a good question. So the idea was that we basically modeled the pointing error, but also we in the actual paper we have results for turbulence as well, right? So the idea was that if the channel conditions change, then the optimal positions will also change, right? And for example, in terms of pointing error, if you have a channel that's dominated by pointing error, then if the pointing error is quite large, then you shift your AF relays. So these are AF relays; these are not decode and forward relays, right? So you shift your AF relays closer to the source, right? So that because the AF relay, it actually accumulates error, right? It doesn't clean the signal, it doesn't regenerate the signal, so it will transmit the same signal, increase its of course after increasing the gain, right? So it will amplify the signal, also amplify the noise, and it will retransmit. So in a channel that's dominated by pointing error, so if you have pointing error, you want to be close to the source if you want to minimize the effect of pointing error, at least in the source relay channel, right? And so we saw that these relays, they try to get closer and closer to the source so that they accumulate less and less error, and that's why we see that the shift towards the source for most of these relays. And of course, if there's no pointing error, then the relays will settle for a uniform distribution, so they're equidistant in that scenario.
Okay,
so
that's quite clear. Okay,
okay.
Thank you very much.
Thank you.
Okay, so I would like to thank Professor Slim and also Professor Salman for the presentation. So thank you very much.
Thank you.
Thank you for the brilliant presentation. Thank you for the tutorial. It was quite complete, and we are quite glad to have a glimpse of your minds regarding how FSO is going to be important for the future 6G networks. Thank you very much. Thank you.
Thank you, Luciano. Thank you for the invitation. I hope we'll have opportunity to meet and network in future conferences. Thank you very much.
Thank you. Thank you.
Thank you.
So
Bye-bye.
this concludes our workshop. Thank you very much for everybody who attended the workshop online and also here at our auditorium. It was very nice to see everybody here. And I also would like to invite you for the next workshop that will happen next year, right? So XMobile is just starting. We're going to have really a lot of events in the near future. Thank you very much.